Hi, so today we're going to talk about Gauss law. And essentially, what we're going to do is we're going to prove that from the electrostatic force. So first, one thing that is important to understand Gauss law is the concept of flux. So what is a flux? A flux is when you have an electric field that is created by a charge, and that electric field from that charge cross a specific surface of area A. Well, the flux of the electric field through that surface is given by the electric field time the area. And here what I did is I put a vector to say that that surface is oriented in space, and right now it's oriented in parallel to the electric field. What specifically I mean by that is that the plane of that surface is perpendicular to that vector that I just drew, A. So technically I could just say the area is a vector A. But we could make that simpler in the case where the electric field is perfectly perpendicular to the surface and just say, okay, I have an electric field of magnitude E, and it's multiplied by the surface area A that it's going through. So that's one of the things, the basic concept we need to understand for Gauss law. It's the flux. Now, what we need to understand next is what happens, what is the flux? So what we want to calculate now is what is the flux of a point charge electric field through a spherical surface, assuming that this charge is exactly in the middle. So we'll redo that. So the charge is exactly in the middle of that sphere, and it creates an electric field to that sphere like this. Right? And all those point charge are the local electric field at the surface. And so you have a sphere, right, that is surrounding that point charge in the middle. And what is the flux of the electric field going through the surface of that sphere? Well, it's gonna be actually a little bit more complicated than our last case, and that's because we have to generalize the concept of flux to an integral. So you have the flux is actually in this case equal to the integral of the electric field time at each point on the surface. So you have element of surface dA at each point on that surface, right? And the surface, because the point charge is exactly in the middle, right? It's exactly in the middle. Then at each point where the electric field gets out of the sphere, like this, the surface is always perpendicular. The surface element is always perpendicular to the electric field at that point, right? Always. So you can rewrite that and say, well, because of that, the dot product of those two electric fields are simply the integral of the magnitude of the electric field at that as a function of the surface area at that point, at a specific point on the surface dA. So you have an element of surface dA, right? An element of surface dA, and you have an electric field getting out at that position that is coming from the center charge. And so we have here what we call a contour. So you have essentially an integral, and what this means here is essentially saying we're integrating over the whole surface of the sphere. That's essentially what that means. And okay, so now what can we do? What is the electric field at the surface? Well, that sphere has a radius, let's say, of r. So from this, what we can say is that, and of course, I want to clarify here that dA, the vector dA, the magnitude is defined as dA. That's what I write here. Okay, and now what we can say is, okay, this electric field here doesn't depend on where you are on the surface. So even if I'm here or I'm here on the surface, it doesn't matter. The magnitude of the electric field is always the same. So you can get this magnitude of the electric field out of the integral and say this. Where now you just integrate over the whole surface to get the overall surface of the sphere. So what you're doing is you just say, okay, I have the magnitude of the electric field time the whole surface. And the whole surface is just A. And what is the surface of a sphere? Well, the surface of a sphere is simply 4 pi r squared. That's what the area of the sphere is. And then the electric field caused by a point charge, we know that too, and it's K Q, which is the charge of the center of the sphere, of the charge at the center, divided by the radius of the sphere square, because we essentially want to know the value of the electric field at a point at the surface of the sphere. And then this is multiplied by 4 pi r squared. All right, so now let's simplify this. Let's rewrite it. So you have we have the flux equal to kq divided by r squared, 4 pi r squared. The r squared cancels out. We are left with 4 pi kq. But k, the definition of k, is actually 1 over 4 pi epsilon 0, right? So from that we can rewrite 4 pi q divided by 4 pi epsilon 0. The 4 pi cancels. We get q divided by epsilon 0. Okay, so then let's rewrite this, all of this. What we deduce now is that the flux through the surface of the sphere is the integral of the electric field dot product the element of surface, the vector element of surface at the surface, so at the specific point on the surface where you evaluate the electric field. And this is equal to what we just found out, which is the charge of the charge at the middle of the sphere divided by the permittivity of the vacuum. And now you essentially arrive to Gauss law. And Gauss law is technically, we proved it for the case of a charge at the middle of a sphere, but Gauss law is always true. Always true as long as you are in a vacuum, right? So if you are in a vacuum, this always holds, assuming, of course, that the sphere is not made of material. So in that case, the flux through that virtual, let's say that imaginary sphere, the flux through that imaginary sphere is equal to this. And this is true for every case where your charge is in a vacuum. It's always going to be true. All right, so that's what I wanted to present today. Hope that you liked the video. If yes, please like and subscribe.